Hi there, this is Tanya Dadasheva and we are here today at Almaz Capital office in Silicon Valley, and I have as a very special guest Dave Ditzel of Esperanto.
Simply put, just so everybody knows, Esperanto has done something that people have been talking about for the last 10 years. And we're really the first to put 1,000 general purpose cores on a chip and to apply it in a very special way for artificial intelligence.
So Esperanto can be very also good in performance-wise and energy efficiency-wise?
Yeah. We've really achieved this vision of having every person to be able to have their own personal supercomputer.
The whole idea of open ecosystem. It's the whole idea of RISC-V and the software ecosystem around it.
RISC-V is on fire, right? It's really catching on. People like the notion of not being locked into one particular vendor here. It's a very big project. It's several years to develop a chip like this, but when you have it, it's very easy to repeat them in manufacturing, and so we're looking for some very good business and for Esperanto to be one of the big players in the RISC-V ecosystem.
Thank you for sharing your vision with us. Hi there, this is Tanya Dadasheva and we are here today at Almaz Capital office in Silicon Valley, and I have as a very special guest Dave Ditzel of Esperanto, the founder and the whole vision behind the company.
Okay.
Welcome.
I'm delighted to be here, and we're so happy to have Almaz as one of our lead investors here, so delighted to come and tell you about what we're doing.
Yeah, actually it's been an interesting journey since 2017. I still remember the first pitch when you came. It was like 3.5 hours. We could not stop. We forgot about everything, about
there
lunch.
There were lots of questions.
A lot of questions, but yeah, it was worth it, right?
Yeah. And simply put, just so everybody knows, Esperanto has done something that people have been talking about for the last 10 years is when can we get a whole lot of CPUs on one chip? And we put over 1,000 general purpose microprocessors on one chip, which is kind of unheard of. In a desktop PC these days, maybe you'll get 4 CPU cores, right? And everybody said, well, the future is maybe you'll get hundreds or maybe even 1,000 someday. And we're really the first to put 1,000 general purpose cores on a chip and to apply it in a very special way for artificial intelligence.
Yeah, but it's not only that, it's also like very energy efficient.
It's surprisingly energy efficient, yeah. We calculated the other day, if you took the standard CPU that's in say a desktop PC and put 1,000, your chip would take about 7 kilowatts, right? And we've managed to do it and make 1,000 CPUs running simultaneously only take less than 20 watts, which is low enough that you can have simple air cooling and really makes it much easier to utilize. And we've been able to do that because of really 2 factors. One is we based our design on a much simpler type of CPU called the RISC-V instruction set, which is a free and open instruction set for anybody to implement. So it's not controlled by any one company. So a lot of our customers really like that. They like open standards. But also Esperanto has a lot of expertise in low power technology. I've been working in the CPU business for almost 40 years, and most of that doing very low power technology. I was involved in some of the very first tablet computers and other things needing low power. And what we realized is if we could make one really, really good CPU core and make it low power, then we could repeat it 1,000 times on a chip and have this incredibly low power to go along with it. And of course, given everybody is very concerned about energy efficiency, and particularly if you have a large data center, sometimes you actually cannot improve the total computing in your data center because you're limited by the amount of power coming in, right? And so unless you improve the actual efficiency and get more performance per watt, you can't just take a computer with twice the performance and twice the watts. It doesn't actually improve the performance of your data center. So energy efficiency has turned out to be a big issue these days.
Absolutely. So it changes how the data centers are cooled. It changes how the data centers are scaled, right? So it's another question.
Well, they can put more computing into the data center they already have. So they're unlikely to actually change the data center. They've already built the building. Yeah. And so I think the nice thing for us is our chip can be used as what's called an accelerator chip. So imagine a giant data center, and in some of these data centers, they may have on the order of 1 million CPU servers. I mean, it's several floors of a giant building, and so these are already built out, and they bought a computer 2 years ago, and now they're going, oh, what do I have to do? If I want more performance, do I have to buy a new computer and replace everything? And Esperanto, we say, no, keep your current computer. If you have an empty PCIe slot in it, we'll just drop one accelerator card into the server you already have, and suddenly that computer will be maybe 100 times faster.
Yeah.
Right? And so they go, wow, that's kind of nice. And so they can use the existing computer to run their operating system and the networking and everything else. But when they want to run very complex problems in artificial intelligence, they can use one of our chips as an accelerator. And so we can provide, on the order of several hundred trillion operations per second. We call them teraops, right, on a single card that plugs into a board. And so that really saves the data center operators a lot of money in terms of not having to upgrade all of their equipment. They can just do a simple drop-in upgrade card.
And those kind of use cases are mostly for hyperscalers right now, right?
Yeah, these are for very large data centers. So these are people with many millions of customers, and when you log into a website, what you'll notice is you're searching for something you want, but along the side you'll see little advertisements come up, right? And what you'll see is, you were looking for a red bicycle for the last several weeks, and suddenly there are advertisements for red bicycles that come up. And you go, how do they know that? Well, this is called personalized recommendation. So they know what your history is, what you've been looking at, and these vendors actually go out, and in the time it takes to draw the web page, they go out and they sell that advertising space. They call the eyeball space on the screen. And so they need to get an answer very quickly in the order of 10 milliseconds, right? 0.01 seconds, right? Of what have you been interested in lately, and who is willing to pay the most money for that, and actually then draw that advertisement up on the screen almost as fast as you can read the screen. Right? So it's a very real-time response issue that they have to respond to, and they have to do this for millions of customers simultaneously. And this is why they say hundreds of thousands or even millions of servers for some of these customers. And these are called hyperscale data centers, maybe if you have on the order of 1 million servers or so. And there's probably maybe 100 to 200 of these data centers around the world, right? So there's really quite a lot of computing put to work here. And servers on the whole take a large amount of the electrical contribution. I've heard it's maybe 2 to 3% of the entire world's electricity is actually going into powering servers, so that you can go to your web page and have find your search for what you want and get the advertising that's tailored just for you.
So recommendational systems, it's one type of models, but Esperanto is not just for that. So Esperanto can be very also good in performance-wise and energy efficiency-wise for other use cases, right?
So recommendation is something that we find very economically attractive. It's very easy to explain to people. But as you point out, we put 1,000 general-purpose CPUs on a chip, and you could do almost anything with that where you have a problem that's called parallelizable, where you want to break it up and to run onto more than one core at a time. So we expect people to do a lot of interesting things with our chip. We can't even imagine all the different uses they will have. But the question is a very simple one. Well, what can you use a computer for?
Yeah,
right?
No, but
and
even
20 years ago, we thought, well, maybe we could do numerical analysis, and today everything is done on computers, right? And so by using this general purpose CPU and putting a lot of them down, we've really achieved this vision of having every person to be able to have their own personal supercomputer. So our chip is small enough, and although we will sell to large data centers, we can also go on a single PCIe card that'll go in the back of a standard desktop PC. Right? And so you could, at your home, have 1,000 CPUs, that 10, 20 years ago, more than most supercomputer centers would have had. And we expect a lot of experimentation and people to play with that and do all kinds of interesting things, from maybe microservices to language translation to, various kinds of scientific experimentation, with a little bit more focus towards artificial intelligence, we expect.
Yeah, but artificial intelligence is in every use case right now.
It's very broad.
You can't imagine a use case that doesn't include it so far. Right. Actually, it's interesting that you mentioned that you expect your customers to go and find these new use cases and new uses. And I want to bring to the attention that it's also the whole idea of open ecosystem. It's the whole idea of RISC-V and the software ecosystem around it, so that it's not just the one company that drives it, it can be driven by any other company,
Many different companies, yes. So in the past, you'd usually look to one company, maybe Intel, to provide a solution. But if you went to a solution based on a chip made from the ARM company, those would be software incompatible, and you had kind of limited choices from each one. So what's new is we have what's called the RISC-V instruction set. The instructions are kind of what drives the software for the computers, but there can be many different implementations. And so far, there's probably a couple of 100 companies who have signed up for RISC-V. And many of those companies are actually making their own chips, all the way from small embedded systems up to giant servers and data center systems. What we find is customers like this notion of openness. That yes, we like your chip from your company, but we see that there's 5 other companies doing something similar, and wow, that's great, because in the future we can just buy whoever has the best chip at any particular year. So it motivates us at Esperanto to continue to have the best chip, because if we don't, somebody else could take our business away by having a customer still stay with RISC-V. And the reason you want to stay with one instruction set is it makes the movement of your software easier, right? And what we find is that although people buy new hardware every 2 years or something, people end up having a legacy of software, and some people are still running software that they developed 20 years ago.
Yeah.
And software that developed today may still be in use 20 years from now. So you want to have some stability in the instruction set, because it makes it much easier to recompile your programs and have kind of a long life for that. And so by having a RISC-V community of hundreds of companies, there will be lots of options here. And so companies feel very safe in moving, although it's a new standard for RISC-V, they feel safer in moving to that, because so many different companies are going to be offering solutions based upon RISC-V, not just Esperanto.
But openness also creates trust, because with root of trust, you can test, and everybody in the community can test and see what's inside. It's in terms of security, in terms of trusting a new company, not Intel that you have been buying for years. It's also like...
Well, you have lots of options, right?
Yeah.
And with security in particular, things have to be tested. And what we see is, a lot of companies, even Intel and AMD are continually doing updates like, oops, we missed something here, there's a little bug, and you have to find that. I think what we'll find with many different implementations of RISC-V, there'll be some very good implementations, and it's possible there could be some weak ones that don't have very good security as well. But I think there'll be a lot of testing and openness, and there'll be a lot of choices. So you won't go to one company and just have to trust that, well, it's a good company, I assume that they'll have very good security and we'll just trust them. Well, mistakes happen. How often do you get an update for your operating system, right? Well, every few weeks there's something new being patched and fixed.
But actually Linux is a very good example. So Linux has been open source for forever. And,
right. And the fact that it's open and reviewed does lend to a sense of robustness and security, because it's easier to examine where might there be a weakness. And also there's a lot of people trying to break it. And when they do break it, the open source community gets together and they end up fixing things. And so the RISC-V instruction set will develop in the same way. We had started off with a nice base instruction set, but there are a lot of people working on extensions and thinking about security issues and how to improve it. So it's going to evolve as an entire ecosystem over the next several years as well.
Yeah, actually RISC-V is not that old. So it's been around for 6 years? So it's you have joined this trend very early on.
And we were one of the founders of what's called the RISC-V Foundation. You can go to a website called RISC-V, RISC-V.org, right? It's an international organization. It's now actually, I believe, based in Switzerland, because a lot of not only companies but countries were very worried that any one company might get control. And so they've tried to make it very international and very safe. And a lot of companies are saying, hey, we kind of like that. We don't want to be threatened with being cut off by any particular control item. And so the instruction set itself is open. Every country, every company is free to do their own implementations. So there's no one trying to limit you in what you can do. It's basically based upon your own imagination and engineering skills to come up with new designs.
And as of now, I think Esperanto is one of the most powerful chips in RISC-V. So the question is...
We think we have the world's highest performance RISC-V chip, yes.
Yeah, and then the question is, when you look at all the other companies that are doing smaller chips, or maybe like TPMs you can put on the board or something, but it's not like the high performance ones.
Yes, so A lot of people started in RISC-V, which is what's called embedded solutions, just one CPU, where the performance didn't really matter. And what we saw at Esperanto, and what Almaz invested in this for, was an opportunity to actually go and be one of the first companies to do the very high end and to do what we call industrial strength RISC-V. A lot of early RISC-V projects were done by universities, and the students did very interesting little projects, but these were not professional CPU designers. And at Esperanto, we've actually gone off and hired our initial set of people who had actually been building microprocessors for large companies, Intel, AMD, a company I started called Transmeta, and others that had 30, 40 years of experience in doing this. And so what we did is we tried to make a very robust chip that large companies like data centers could really depend on in the same way that they depended on other manufacturers in the past.
Yeah, actually, that's also a very interesting story. So, how do you feel it's different from Transmeta's experience? So, going to openness, going to RISC-V.
Well, there are some things in common. You know, Transmeta took the x86 architecture that was initially started by Intel and later followed by AMD, and we built some of the first very low power versions. I think we were the very first company to put a 1 gigahertz CPU in a standard Windows notebook computer, right? And so the issue of energy efficiency was important. And at Transmeta, we built one CPU, and we spent many years putting that together. So the challenge at Esperanto in putting 1,000 CPUs on the chip, and we actually have different types of CPUs as well that we've done, was a really big challenge. So just the amount of scale made it very different. We picked a different instruction set. At Transmeta, we used the x86 instruction set, was popular for Windows, and here we're using RISC-V, which tends to be more used with Linux and for other specific accelerator software. So it's a similar experience in terms of a startup in that you're going to try and beat some of the big names in the industry. We're competing with Intel, AMD, NVIDIA, and a number of private companies who are building their own chips for artificial intelligence. But our view is very simple, that even if there's a private company that has their own CPU design, right? If there's a better chip on the market, there's always a make versus buy decision. And so we feel if we can build a very good chip, we can go in and there's lots of different uses. Each chip tends to have something it's very strong at and other things it's weak at. And one of the nice things we have by basing our design on the RISC-V architecture is it's very general purpose. So we may not have the peak performance on any one particular benchmark, right? There's one out there very popular now called ResNet 50. And 20 years ago, it used to be called the Drystone benchmark, and nobody actually runs Drystone to do anything, but it became very popular, and so people optimize their hardware to do that. And the same thing has happened now with the ResNet 50 benchmark. It's good for image classification if you want to, say compare two photos versus each other, and that's one important part. But artificial intelligence is very broad, and the algorithms for artificial intelligence are changing so rapidly that what we're seeing is the people who went and designed very specific hardware to get a really great performance on one benchmark, the benchmark and the software that needed to run is changing so fast that that software no longer works with their hardware. Yeah. So our approach was very different in saying, hey, if we can take general purpose CPUs and get the power down and the performance up high enough, that's going to be so much easier for people to program, and it can keep up with the change in algorithms, because then you just take a normal algorithm and you just compile it to the chip, right? And you don't have all the difficulties you have. You hear about the difficulties for people who try and encode graphics processors, and it was very difficult to do all the programming because you have to program in a very specific way for this very specialized hardware. So we're trying to take the vision that people have, saying, why can't I use my general purpose computer and just give me 1,000 of those CPUs, right? And so really we're bringing that kind of environment to a single chip now. And we're the first to have done that, and again, we're very excited about that, to be the highest performance RISC-V chip out there. And again, let me just talk about the status. We've just received our first silicon back. It's in 7 nanometer TSMC technologies, one of the most leading edge technologies in the world right now. And so it's very exciting doing the bring up and testing the software and testing the chip. And so we're going to have a very exciting next year as we go from our development phase into actually the manufacturing and sales and delivering of systems.
Yeah, very excited to hear what the first customers will think about it and how do they adopt the internal ecosystem for that. Yeah, that's for sure. So anything in particular that you didn't expect when you started it, like 2017, that was a surprise? Or that the industry just changed during this year? It definitely accelerated.
I think the acceptance of RISC-V has gone much faster than we expected. I've done new instruction sets over my whole career, and typically it's about 10 years from when somebody introduces something to when you can start to really catch on. And I think RISC-V has seen an adoption rate that's maybe at least twice as fast as that. It's maybe been 5 or 6 years since it was introduced, but it's started to get very good adoption. Really not a lot of systems actually in production yet, but a lot of companies who have designs they've just finished, they'll be bringing it out, and I think over the next 5 years, as we said before, RISC-V is on fire, right? It's really catching on. People like the notion of not being locked into one particular vendor here, and so there's a lot of interest around RISC-V. Particularly universities who found before that they couldn't even teach students because they couldn't develop the simulators and other things because everything was proprietary. And so here all these models are open. In fact, Esperanto has contributed one of our reference models for a CPU to another organization I'll pitch here called the chips.org, right?
Alliance, yeah.
And RISC-V.org is about establishing the instruction set, really a manual for what the software generates. And chips.org is for open source hardware, and actually open source software that are tools to help people make chips for free. Not all the chips are free. You still have to pay for the chips.
Yeah,
right?
It doesn't kill the business model. Yeah.
Right, but certainly having this very wide community has made it easier for us to build something that otherwise would have been just infeasible in terms of the complexity before, because we can leverage that entire community. We get to use the RISC-V compilers. We had people developing IP for debuggers and other things that we could acquire and put in our chip. Although we have done something a little unusual, which is designing our own RISC-V CPUs. A lot of companies will go out and they'll just try and license some IP or get a chip that was developed at a university and try and figure out how to utilize that. So we've really done two kind of what we call industrial strength RISC-V CPUs that we put in, our Minion and our Maxion. The Minions are the little ones, there's 1,000 Minions all doing work, and the Maxions, we have a few. We have 4 of these very big cores, more traditional type of CPU cores to program. And those would run things like the Linux operating system.
Yeah, I remember the pictures of Minions actually from the cartoon in the first deck. So to explain to us what how it works, how they form into shires.
Well, really, and it's about parallelism. A lot of people don't really appreciate, when we build an individual new CPU, really every generation, maybe you go 20% faster or so. But when you can use parallelism, you can get 1,000 things working in parallel. And so you think of, workers doing construction. You have 1,000 workers doing construction. Sometimes you can work 1,000 times faster if you have work that can be done completely in parallel. And so, being able to get 1,000-fold increase in performance is really quite a leap forward, particularly when you can do this on a single chip.
Yeah. And the big ones are to distribute the task, to optimize it,
It's developing all the software to distribute. One of the reasons we started with artificial intelligence is we can provide what's called the machine learning infrastructure, the compiler, the other things here, to take a problem written in a high-level language like PyTorch, right, and take that kind of a model, and we can do all of the mapping down below. To use the parallelism in a more general purpose way, you can start and you can program each core individually, but that's a lot more work for users. So that will take a little bit more time to develop, but when we see hackers out there and other software developers go, wow, 1,000 CPUs. Ooh, we think people are they're gonna find a lot of initiative to go out and find all kinds of interesting things to do.
No, that's for sure. The ecosystem is like no other. Both in terms of different foundation and alliances, and also with just software developers community.
Yeah. So it's a very big project. It's several years to develop a chip like this, but when you have it, it's very easy to repeat them in manufacturing, and so we're looking for some very good business and for Esperanto to be one of the big players in the RISC-V ecosystem.
Yeah, they're doing the same. So let's continue the journey together and see where it leads us.
Well, thanks very much for all the support we've had from Almaz.
Yeah, thank you for sharing your vision with us.